Okay, so hello and welcome back. So in this video, basically I want to talk about the RL circuit. In the previous videos, we did an experiment with an RL circuit, and we showed how a low-pass filter containing an inductor and a resistor works. Now we want to do the same thing for a high-pass filter made using an inductor and a resistor. So basically a high-pass filter basically looks something like this. So this is a high-pass filter. You have a resistor and an inductor, and these two are basically connected in series. And basically what happens here is that as you increase your frequency, the inductance of the reactance of this inductor increases, and with that basically the voltage drop across the inductor is going to increase, and then that's going to be basically this graph over here that you see. This is V of out, this is V of out, and this is basically F of in. So this is frequency, this is output voltage. As you increase your frequency, your output signal, the amplitude of the output signal is going to increase. And again, it's been called a high-pass filter because you see at high frequencies much of your signal is passing through the filter. There is also some phase shift and other things about the circuit that we'll go through as well. So the circuit that I want to use here is this. Basically this, I have a resistor and an inductor. So this is my inductor, this is my resistor connected in series with the inductor. We will inject the signal into the resistor here, and then this lead over here becomes the ground, and then this lead where the two components are tied together, that becomes your output, reference to the ground. So then I'm going to start with I have basically two function generators. One of them goes up to 2 megahertz, one of them goes up to 10 megahertz, and but the one that has a higher frequency is the signal coming out of that one is not very clean. So I want to start with the one with that goes all the way up to 2 megahertz, and then we will take it from there. And basically while I'm doing this experiment, we will collect some data, and then we will make it basically in the next parts of this video we will do some analysis and calculation using this data as well. So now let me bring it down over here. Okay, so this is my signal generator. I set it to 1 and then go all the way down to, for example, here somewhere. And this is my oscilloscope. And this is the output of my signal generator. I want to tie it up to this counter as well. So we can look at the frequency as well. Okay, so we will start with a pretty low frequency, and you see in this high pass filter, as you increase your frequency, your voltage is going to increase. So in the beginning we will have lower voltages, and as we go, basically as we increase the frequency, the voltage is going to increase. So then what I'll do over here is, basically this is my circuit, and this is the output coming from the signal generator. I connect the output to the resistor, the ground to the inductor, to the end of the inductor, and this is channel 1 of my oscilloscope. With that I will watch the input, and this is channel 2 of my oscilloscope. With that I'll watch the output. Okay, and then if now you go to take a look at the oscilloscope, you must see, go to norm and channel 1, and I'm not seeing anything here. I think the voltage is not at all high. So this must be, this is my output. My input is this must be somewhere over here. Okay, so it cannot trigger. I have to use the auto mode so that the trigger can somehow work, because the frequency is actually somewhere around 1 Hertz or so. And you can see that my output is at about 10 millivolts. My input is at about 2.5 times 2. I think my input is at about 5 volts peak to peak or so. But these readings at the beginning of the spectrum of the frequency are not very reliable, so we don't have to pay much attention to that. So if I increase my frequency to somewhere about 10 Hertz or so, now you see that the frequency is about 10 Hertz, something like this. Okay, so that's 10 milliseconds, and I get one complete, basically the width of the screen for one complete cycle. That means that well, if I take 1, 2, 3, 4, 5, 5 plus 5 is equal to 10 horizontal units for one complete cycle, give or take. Okay, 10 horizontal units, 10 times 10 is equal to 100 milliseconds is your period. So 100 milliseconds would be 100 milliseconds, and if you take the reciprocal of that, 100 milliseconds would be 1/10 of a second, and the reciprocal of that is 10, which means 10 Hertz. So that means that my frequency is somewhere about 10 Hertz. And your output, you see, it's somewhere about about 10, so 20 millivolts peak to peak. So we can start at somewhere about this frequency. So this frequency is safe for us to begin. So at somewhere about 10 hertz, the input, and now still I cannot let me just for a second, let me increase the frequency so I can read the input voltage magnitude, and then I'll come back and see what's going on. Because with this, on this frequency, I cannot trigger on anything, so I cannot read the voltage over here. So I increase the frequency, and now I can read the output voltage peak to peak, and that's about, so I'm at 5 volts, so 1, 2, 3, 4, 4.8. So 4.8 times 5 is equal to 24 volts peak to peak or so. So my input is at 24 volts peak to peak, but basically that is V of in 24 volts peak to peak, V peak to peak, and my output is at, we were at 10 hertz or so, okay, and my output is at this is my output, somewhere about 1.4 times 10 is equal to 14 millivolts. 14 millivolts peak to peak. Not very accurate, but just some value. Okay. The next thing that we have is that we can increase the frequency a little bit. For example, go to somewhere around 20 hertz or so. About 20 hertz or so. At about 20 hertz, your output, your input level has not changed. 1, 2, 3, 4. It's actually 1, 2, 3, 3.8. 3.8, right? 3.8 times 5 is equal to 19. I'm sorry, the input is at 19 volts peak to peak. So I'll just leave it at 19. Okay, so 19 volts peak to peak. My output is at somewhere about 1.4 times, around 14 millivolts or so. So 19 volts peak to peak and 14 millivolts. That's about 20 millivolts, 20 hertz. So if I go back down here, 100 times 0.2, that's about 100 millivolts or so. So at about 40 millivolts, I have kind of the same output. 60 millivolts, I have kind of the same output. And now it's kind of, now at, for example, somewhere about 100 hertz, the output is at about, well, kind of the same thing. And let's go to, for example, 100, 1.2 times 100 is equal to 120. Not much change. Okay. not changed. So I come back down here. I come back down here and go to basically 0.2 times 1K is equal to 200 hertz or so. So still the output has not changed. So I increase the frequency a little bit, and still, so right here it's kind of changing to 1.246 and 1.8 times. So it's around 18 millivolts or so. 18 millivolts and my input is the same input, 19 volts peak to peak. The frequency is about, you see our frequency is, you can read it over here. I don't really trust this counter at these low frequencies. It gives me garbage value, so I don't trust it at these frequencies. So I usually do it on the screen manually. So if you come down here, you probably even, but the problem is that if you make it if you zoom in horizontally too much, then you will not be able to see the middle part of this trough, for example. So I would go back here. So now this way I can see the symmetry of the wave, and so I can go exactly between these two waves, so that I can go exactly at the bottom of the trough. So you see I can move it over here and take a look at the symmetry. And now my signal is at basically 2.6 times 0.5 milliseconds. 2.6 times 0.5 milliseconds is equal to 1.3 milliseconds. And if I take the reciprocal of that, my frequency is 770 hertz. 770 hertz, and you see that the counter is giving me 760 hertz. It's giving me 760 hertz. So that's why I say that I don't trust this counter at low frequencies. I guess above 2-3 kilohertz or so it's going to be fine. Okay, so now if I increase my frequency to somewhere about 1.4, so it's 1.4 kilohertz or so, still the output is increasing. So it's about, I don't know, 1.2 times 20 millivolts. 1.2 times 20 millivolts is 24 millivolts. 24 millivolts. The same input, the frequency is about 1.58. What is my time base? 0.5 milliseconds. 1.58 times 1.5 milliseconds. And take the reciprocal of that. 1265. Okay, good. 1270. I take it as 1270. 1.27. 1.27 kilohertz. Okay. So from this range, starting from this range, you can kind of start trusting the counter. Below that, it gives you garbage value, kind of garbage. And then when you get very close to, for for example 10 hertz or 15 hertz, in that range it's not trustable at all. So okay, so now let's increase the frequency a little bit, and you see in this range it's not changing much. I read it over here, for example. I read it over here, it's around 1.6 times 20 millivolts. 1.6 times 20 millivolts. It's 32 millivolts. It's 32 millivolts at 1.9 kilohertz. And then let's go all the way back down here. Let's go to 10K, and let's go all the way to 0.4 times 10K is equal to 4, around 4K. So now your output is at about 20. So 21 to 2.6 times 20 is equal to 52 millivolts. Okay. At 3.4 kilohertz, your output is at about 52 millivolts. And then keep increasing your output. It's rising very sharply. It's rising very sharply, and you see over here you can read your output here as 1.4 times 50 millivolts, 70 millivolts or so. 70 millivolts. That's at 4.9 kilohertz. And then if you keep increasing your output here, you see it's rising very sharply in this area. Very sharply. So now you're at about 1.8. 2 times 50 is 100 millivolts. 100 millivolts at 6.9 at 7 kilohertz. At 7 kilohertz. Keep okay. And it's about 1.6 times 0.16, so that's 160 millivolts or so at 11 kilohertz. Okay, and over here, let's increase the frequency a little bit. It's 1.2 times what? I'm sorry, this is 2.2, so 2.2, that's 220 millivolts. 220 millivolts or so at 15.7 kilohertz. And then increase a little bit more, you will get so 2.8 280 millivolts or so. 280 millivolts at 20 kilohertz. At 20.3 kilohertz. and then I go all the way back down here, and I have to decrease this a little bit. Put it over here, and make it a little faster. And then if you increase your, I move this input out of the screen for now, so you can see the output much better. And then at 59 kilohertz, your output is at about 1, 2, 3 points. Take it as 4. 4 times 0.2 is equal to 0.8 volts. 0.8 volts, that's 800 millivolts. 800 millivolts at 59.5 kilohertz. 59.5 kilohertz. And then if I keep increasing this frequency, you see that my frequency is, right now my output is at about 2.6 times 0.5 volt is equal to 1.3 volts at 95.4 kilohertz or so. And then keep increasing this a little bit over here, probably make this a little faster. And then now you're at 1, 2, 3, 3.7 times 0.5 is, you're at 1.85 volts. 1.85 volts at 144.7 kilohertz. And then you can still increase this frequency over here. Now I'm at about 205 kilohertz, and my output is at about 1, 2, 3, 4, 5, 5.4 times 0.5. I'm at about 2.7 volts or so. 2.7 volts at 205.7 kilohertz. And just to make a quick check over here for the counter over here, let's see if the signal is, if the frequency is actually right. So let me move this thing over here and move this thing over here. Okay. And now, right now, let me move this up here and move this over here. Okay, and move this up here. So this is 1, 2, 3, 4, 4.8. 4.8. 1, 2, 3, 4, 4.8 horizontal units times 1 microsecond. So 4.8 microsecond, 1 over 4.8 microsecond is equal to 208,333. It's a little bit off. We make another reading here. Do another reading here. Okay, so you see I am right here, and I suppose I go 1, 2, 2.2, 2 point, let's make it 2.2.4 for example. Actually, I'll make it 2.4. 2.4 times 2 is 4.8 microseconds. If I take the reciprocal of that, it's 625 times is 208. It's a little bit off. Or it might be because of the fact that this is not a clean sine wave. You see over here, this is actually not a clean sine wave, or of course this is coming out of the filter. But if I move this down here, and my input is cleaner. It's clean enough. There's nothing wrong with my input. See, everything is kind of fine, except for some problems over here. You see over here, there is some problems over here, but still, this counter is a little bit off. You have, I mean, if you want your frequency to be, well, as exact as possible, you need to most probably just make a reading over here. Or what the other thing that you can do is that I have another oscilloscope here, and this is one of those PC based oscilloscopes that you connect to a via some USB port. You have to connect it to a PC, and then you have 2 channels over here. This must be more trustable. I mean, the reading, this must be calibrated because I got this new. But the problem is that these are not very easy to, I mean, all the time the software is freezing and so on and so it's just a whole bunch of, it's a lot of trouble. But anyway, now we are at about 205.7, I take it as 205.7 kilohertz or so. So I'm at 2.7 volts, and you know, the experiment that we are doing here is more about the overall general behavior of these filters. It's not about exact readings or exact data over here. So it's okay if the counter is a few kilohertz off. That's not the problem really. Okay, so now that is my output at 205. So you have 1 2 3 4 1 2 3 4 5.4 times 0.5 is equal to 2.7. Okay, now if I increase this a little bit all the way up to 1 meg, and if I increase this a little bit, right now I'm at 1 2 3 4 5.3 volts peak to peak. So at 407 kilohertz, my output is at 1, 2, 3, 4, 5, 5.3 volts peak to peak. So if I increase this a little bit at about 787 kilohertz or so, my output is at 1, 2, 3, 4, 5, 5.5. That's at 787 kilohertz. And then I can increase this a little bit more, and you can see over here it's still increasing, and now it's stopped. So I do it again. So pay attention to the output. So you see the output here is at about about 10 volts peak to peak, right? And that is about 728. Okay. I guess I made a mistake over here. Let me see, 787 kilohertz. And about 780. My output is at 2.5. So 2.5 times 5 is at about 12.5 volts peak to peak. I'm sorry. At 802. At 12.5 volts peak to peak. Okay, and then if I go all the way up to, you see over here what happens as I increase the frequency, I get all the way up to here, about 1.3 megahertz or so, and my output here is at about the same as the input, kind of the same as the input. So 1, 2, 3, 3.8, and the input is basically the same thing. You see my input, they are basically both on the same scale, but my input is above 4 units or so. So a little lower than the input. Okay, so and the exact voltage is 1, 2, 3, 3.8. 3.8 times 5 is equal to 19 volts peak to peak. Oh, 19 volts peak to peak, and the frequency is 1.3 megahertz or so. And now you can see that the input has actually changed. The input is 1, 2, 3, 4 times 4 is equal to about 20 volts peak to peak. So we started with 19 volts, but as you increase the frequency, your input kind of changes on this generator. It's not it happens on this generator. So and then as I increase the frequency here, as you can see, the input is kind of, let me bring this down. Okay, so now the input, take a look at the input and the output. So as I increase the frequency over here, the input is not changing, but the output is decreasing about at about 2 megahertz or so. So from basically from all the way up to 1.3 megahertz, you're at the peak of the voltage, and then it kind of keeps decreasing, but I don't know what happens after 2 megahertz. So what I'm going to do, I'm going to actually disconnect this generator from here and connect my circuit to the other generator. Okay, so the other generator is here. I connect it to this circuit. Connected here, and then I guess I need to go all the way to 1 meg here, and then the frequency. Okay, and then my input. Let me watch this. So what's going on this input here. This is channel 1. This is channel 2. Okay. Now this is my input, and as you can see, the frequency is, I move it to 1.5, and I connect the other counter to here so we can see the frequency as well. So I'm about 1.4, 1.2 megahertz or so, just to make sure that everything is fine. So this is somewhere over here. So you have 1, 2, 3, 4, 4.1 times 0.2 microseconds. 4.1 times 0.2 microseconds, and take the reciprocal of that. It's about 1.2 megahertz. Okay, so the frequency is okay. I mean, the counter is showing me okay, everything, and the output voltage, I want to make it about 20 volts peak to peak. So 5, so this is 1, 2, 3, 4. I make this 20 volts peak to peak. Okay, so now this is 20 volts peak to peak, and my output is about 2.123. 3 times 5 is no, that's I'm sorry, that's 15. That's 15. That's 20 volts peak to peak, and my output is at 3.6. 3.6 times 5 is about 18 volts peak to peak. Okay, so now I'm at about 1.2 megahertz or so. So if I increase the frequency here, you see what happens is that the input actually keeps decreasing, and that's, although basically what happens is that you're basically on this signal generator, this signal generator is not perfect, of course, And you see that if I go to about 1.2 megahertz or so, my output is about 20 volts peak to peak. Okay, but but what happens is that right now at about 1.2 megahertz, at about 1.2 megahertz, my input is at 20 volts peak to peak, and my input is 20 volts peak to peak. My output is at about 18 volts peak to peak. Now if I increase the frequency, you see that basically my input starts decreasing as well, and that's something just related to the signal generator, has nothing to do with this experiment. Meaning that if you watch the output of the signal generator connected to nothing, just connected to the oscilloscope, you will see the same thing happening on the signal generator. But then with that, with this circuit, you would actually expect that your output would simply keep increasing and get to the basically to the power supply voltage at least, which is about 20 volts or whatever the power supply is at that point in time. But now you see, as I go, you see this is the point, this point over here. You see, this is, I'm now decreasing, and now if I keep increasing at this point, somewhere about 1.2, 1.3, the signal comes to the peak. The voltage versus the frequency comes to the peak, and then it starts decreasing actually, and decreasing and decreasing and decreasing and decreasing, and now I'm at about 5 megahertz or so, and decreasing and decreasing and decreasing, and now I'm at about 10 megahertz, and that's basically how this circuit behaves. Okay, so now basically that's how this circuit behaves. I don't really know why. It just behaves like that. I don't know due to what it behaves like that. So now in the next video, we will basically analyze our data and probably do a couple of calculations. But before we do that, we do need to do a couple of readings regarding phase shift, and then we will take it from there. But before I go any further, I take a few minutes rest, and then I'll come back. We will do some phase shift readings, and then we will get to the rest of this experiment. Okay, so now about the phase shift. So you know that the phase shift does depend on the frequency. So we will do the rest of this experiment using this signal generator here, and since if you're interested to know, it's a WaveTech model 142, and that goes all the way up to 10 megahertz. Okay, so we will do the rest of this for the phase shift using this signal generator, because there is no need to switch around between the two generators. And so what I'm going to do, what I'm going to do is that I'm going to go back down here in the range, and now I'm at about 10 hertz or so. I cannot see anything, of course, and there is not much output here either. So I'm going to switch back to times 10, for example, something like that. And I think at this frequency there is not much phase shift over here. You see over here, it's still I mean, the oscilloscope is kind of, I mean, it's surprising that it can trigger actually, but there is not much phase shift here. And if I multiply the frequency by a factor of 10, you see I'm about 1000 hertz, 1 kilohertz, and still there is some phase shift here. Okay, so it starts at probably about 500 hertz or so. No, I'm sorry, 50 hertz. This is there I'm about 50 hertz, and if I bring this signal up, there is no phase shift here, and this is all the way up to 100 hertz. And if I go down here and multiply the frequency by a factor of 10, and now if we bring everything down here, okay, and move this over here, there is still no phase shift at 100 hertz, and the phase shift kind of starts at 200, at 100 hertz or so. The phase shift starts at 100 hertz or so. Starts at about 100 hertz. And then right now there is not much phase shift, and you see that this is my output. The top wave is my output, and my output is still red. There is no phase shift still, but if I increase the frequency a little bit, you see that the output is leading. You see, the output is leading by probably, I don't know, if this is 360, this is 180, and that would be about 20-30 degrees or so. And now the phase shift is increasing, and if I multiply the signal by the frequency by a factor of 10 and move this up here, I am about, so you see the phase shift is over here, and now the phase shift is not changing anymore. It's not changing anymore. Okay, so the phase shift, I think it happens between 100 hertz all the way up to about 3.5 kilohertz, and then after that you don't have much phase shift there. See over here, the phase shift is not happening anymore. It keeps constant, and both of the waves are changing together in frequency. So you see, as I increase the frequency, so the phase shift actually happens. And it's interesting to note that the phase shift happens because the frequency, because as you change the frequency on your input, of course the frequency on your input is changing, is increasing. But then the phase shift happens because your output is not changing in frequency, and as a result of that you have phase shift on you have the phase shift between the two waves, your output and input. but then it seems that it happens between certain frequencies for certain inductors, for certain values of inductance, for example, and resistance coupled together. So now if I, for example, multiply now if I keep increasing the frequency, as you can see, the phase shift is not changing anymore. Okay, again I go back and multiply by 10, again increase the frequency. The phase shift is not changing anymore. Okay, so right now I'm at about 840 kilohertz. Go back over here and then times 10, and oh, now it's kind of changing. Oh, at about 1 megahertz. Okay, at about 1. So you see over here, what happens is that now I'm about 0.8. At about 0.8 kilohertz. You see, this is my output, and my output is leading, right? My output is leading, and so this is my output, and my output is leading, and it is supposed to be yes, it's supposed to be leading, of course. You see, my output is leading, but if I increase the frequency starting from somewhere around 800 kilohertz and go, you see, at this point the phase shift cancels itself out at 1.3 megahertz, and that's exactly the frequency at which the output voltage started to fall down. Okay, so right now you see that your output is at this is my output, this is my output voltage, the one that I'm moving, and right now if I increase the frequency from this point, you see the output is getting smaller and smaller. Okay, and but what happens at the same time is that the phase shift is cancelling itself out at this point, which is exactly 1.4 megahertz, 1.34 megahertz. And then if I keep increasing the frequency above that frequency, now the output is actually now the input is actually leading, not the output. Now previously the output was leading, now the input is leading, and you see what happens here is that the output is actually leading, and I can keep going all the way up to 10 megahertz, and that's basically what happens. So that's basically what happens in this circuit. Now, before we wrap this up, I think the above 1.3 megahertz, that's some sort of weird behavior of this circuit, that basically the output is actually lagging, because the output is supposed to be leading in this circuit at least below 1.3 megahertz, and then also above 1.3 megahertz your output starts diminishing. So I'm going to go somewhere below 1.3 megahertz or so, somewhere about, for example, 500 megahertz or so, and I'm going to make a reading over here, and then that's what I'm going to do. Okay, so right now this is my input, and which is lagging. This is my output, which is leading, and the frequency right now is let me make it reading over here, so it's about 1 2 3 1 2 3 3.4 3.5 3.5 times 0.5 microseconds, 3.5 times 0.5 microseconds, and take the reciprocal of that. It's 57 571 kilohertz. 571 kilohertz. At 571 kilohertz, what is the phase shift? So first of all, at 571 kilohertz, the input, the output is leading. Okay, and the output is leading, and by how many degrees? That you can find out by basically this way. So if you basically make some adjustments here, so that your waveform basically is centered about this line, and then what you can do is that this is one complete cycle of this wave. So this is 1 2 3 point, bring it up here, bring it somewhere up here, to somewhere over here, and then you can see that you have 1 2 3 3.4 3.5, right? So 360 degrees, so 3.5 horizontal units corresponds to 360 degrees. That's basically the period of a sine wave. And so now what is the phase difference of these two waveforms? It's actually, you can bring the input wave over here and the output wave over here, and make a reading, and basically put them in this position, so that you can, and it's about 0.6 horizontal units. So the difference is 0.2, 0.4, 0.6 horizontal units. So then if 3.5 horizontal units corresponds to 360 degrees, 0.6 horizontal units is going to correspond to 360 times 0.6, and the whole thing you have to divide it by 3.5, divided by 3.5, which is equal to 61.7 degrees. Okay, if you didn't understand what I did here, let me actually do it over here. So basically what I did is that in order to calculate something like this, you can simply use simple proportions in order to get that. So what you can do is that on the oscilloscope screen, based on the based on the input waveform, I saw that one complete cycle of the input waveform was occurring in basically one complete cycle of the input waveform, which is 360 degrees, was occurring in 3.5 horizontal units. That means that 3.5 horizontal units correspond to 360 degrees, right? So if 3.5 horizontal units corresponds to 360 degrees, then we went in and basically measured the phase difference between the two waves, meaning that you put the wave over on the screen, and for example, this is your input wave, this is your output wave. You kind of need to basically adjust them somewhere so that you can make a good reading. So I adjust them against this horizontal line, and on this line there is some graduations, and on these graduations you can actually read pretty well. So I put the two waves over here, and then adjust this input wave about this vertical line, meaning that I adjust this input wave, this one. Sorry, this is the output one. So adjust this output wave about this vertical line. You can do any of them, meaning that you can basically do it this way as well. Doesn't matter. And then you have to read the difference over here. Otherwise you can do it like this and read the difference over here. So that's basically now 0.2, 0.4, 0.6. 0.6 horizontal units is the difference between these two peaks, and these two peaks are related to the two waveforms. So now that you know that the difference is 0.6 horizontal units, 0.6 horizontal units, it doesn't matter what that translates to in terms of seconds and milliseconds and microseconds, it doesn't really matter. So now that you know that the difference is 0.6 horizontal units, that 0.6 horizontal units corresponds to some angle as well, because 3.5 horizontal units corresponded to 360 degrees. So 0.6 horizontal units proportionally corresponds to some angle as well, meaning that, for example, if 3.5 horizontal units corresponds to 360 degrees, then half of that half of 3.5 corresponds to half of 360 degrees, which is 180 degrees, right? So now, in order to calculate this, you can use as a fraction over here and write, for example, 3.5 horizontal units to 0.6 horizontal units is the same thing as 360 degrees to x, for example. And then to calculate x, you can cross multiply, meaning that x times 3.5 horizontal units is the same thing as 360 degrees times 0.6 horizontal units, and then horizontal units and horizontal units will cancel out from both sides of this equation, and then x is equal to basically 360 degrees times 0.6, 360 degrees times 0.6 divided by this number, which is the coefficient of x here, 3.5. And if you do this calculation, 360 times 0.6 divided by 3.6, actually this is supposed to be 3.5, I'm sorry, 3.5, that is equal to 61.71, that is equal to 61.71 degrees. And that's basically how you calculate your phase shift on some basically analog oscilloscope. So 61.71 61.71 degrees. That's your phase shift. Okay, so that is basically that. So now let's go in and take a look at our data and do a simple graph of the output voltage versus the frequency, and do some calculations there, and do some calculations with the phase shift, and then we are done with this circuit. So I'll see you in the next video. Thank you.